Welcome to the 19th lecture in 303 heat transfer. We'll start with a new topic today, and that's called convection. So convection's the most widely applicable mode of heat transfer in energy systems and in mechanical engineering particularly. Of course, all of them are required, all three modes, but convection is the most dominant mode of heat transfer in most of the applications we work with. So this topic is extremely important. So we'll start with this topic today. We briefly touched upon convection during our initial lectures, first few lectures, where we talked about the mechanism of convection. So let's do a quick recap. We always have been taking the example of this flat plate. So you have a flat plate on which there's some fluid that is flowing over it. And what happens is, let's assume that this plate's hot, and we're trying to cool it by putting it in a cold fluid stream. This T infinity is less than T surface. We have a T surface here, which is the plate temperature. So what we see is that since we already know fluid mechanics, the no slip condition. So assuming that condition is valid here, so on the surface, the fluid velocity is 0. So in this two-dimensional situation, on the surface we have u equal to 0 and v equal to 0. So the fluid molecules which are touching the plate's surface are at 0 velocity. And as you move up, then you see that the velocity profile has developed, and then finally you have a boundary layer beyond which u is equal to u infinity. To draw the velocity boundary layer, so this is my u profile, which goes from u equal to 0 at the surface to u equal to u infinity beyond the boundary layer. So that's how we define the boundary layer, where 99% of the surface effects have penetrated into the free stream fluid. Now, what happens is just the fluid molecules which are just above the solid surface, they are stationary. So the only mode of heat transfer that can happen through those molecules is conduction in this case. We're not assuming, we are assuming there's no radiation here. So conduction is the only mode of heat transfer that happens from the surface to the first layer. And then just above that, you see that the velocity profile is there. So these jiggling molecules just above the plate surface, they hit the molecules above them because of the Brownian motion, and then the molecules above them become hot as well because of this conduction. And then since they are moving, they move and take away the heat and allow the fresh cold molecules to get replace them, which again get hit by the lower this layer, which is there's no layer as such which is not moving, but we are discussing in the sense of layers. So the molecules which are just above the surface, they hit that cold layer again, which become hot, and then they move on. So this is how you have convection happening in this situation. Okay, so this is the mechanism. So we said that convection is nothing but conduction, which is just above the surface, plus advection. So this bulk transport of the hot molecules and replacing them in cold molecules is called advection. So both are important. In fact, that is what helps us define the value of the heat transfer coefficient, as we'll discuss again today. The examples are many. I mean, one of the most common examples I talk about is the use of fans. So when you're feeling warm, you switch on a fan, and that although the air around you is still cold, well, colder than your body temperature, But when you switch on the fan, you feel much more cooler. So that increases the rate of heat flow from your body, which ultimately results in the feeling of um, the cool feeling. Okay, so the rate of heat transfer from your body to the ambient around you increases as you switch on the fan. That basically means that you increase the heat transfer coefficient because of convection by increasing the flow rate. Another very useful example is what happens in your semiconductor devices, your computers and your mobile phones. Well, mobile phones, on computers mainly, because you have a fan to cool it. So you have a processor which gets extremely hot when you are clocking it at a very high frequency, and this solid processor, semiconductor surface becomes extremely hot. You have a heat sink which is attached to it using a thermal paste. And that heat sink has nothing but lots of fins in it, and then you have a fan which blows air across the fins to cool the fins down, which ultimately cools down the processor surface as well. So that allows increased rate of heat flow from the processor, preventing that processor to become extremely hot, which can ultimately result in the failure of the material. So convection is extremely important, and we must study we must study the mechanisms of convection, what how different parameters of flow affect the rate of heat flow from bodies because of convection and so on. And then we must also learn how to use the convection, heat transfer coefficient values and so on for real life situations for designing engineering devices. So typically, the discussion on convection is in two parts. The first one being on the mechanisms, which we'll be talking about in the next 2 or 3 lectures, which is heavy in mathematics. The same way you had boundary layers, equations, solving them, and ultimately getting the relations for the value of heat transfer coefficient. The same way you got the relation for laminar flow for boundary layers, skin friction coefficient. Okay, similarly, and then after that, we will experience a lot of correlations which have been developed based on empirical studies for different geometries, different situations. So if our laminar relations that we will analytically develop are not applicable, or are not applicable with a decent approximation, then we'll have to go to these correlations. So ultimately, for solving a problem in engineering, we start with the first guess where we assume some analytical correlation to be valid, and that gives us some sense, some intuition of some feeling of the amount of energy that's leaving the surface. And then to improve our calculation, we pick up further correlations from the handbooks that have been the correlations that have been developed by the others based on lots of empirical studies for different geometries and situations. Okay, again, to understand the convection, the mechanism of convection, we must first understand the mechanism of flow happening over solid surfaces. So for that, we'll do a quick recap of our fluid mechanics, especially the topic on external flows, where we had these boundary layers developing over surfaces, and then we'll very smoothly transition to the discussion on um, thermal um, convection. Any questions before we start? The first topic we'll be discussing is the velocity boundary layer. I'm sure everybody remembers this figure, extremely popular. So we have a free stream velocity u infinity, and then in the path of this, we put a flat plate where we have a leading edge here, and then you see that a boundary layer develops. Your u, which is your x component of the velocity, is a function of y. So the y coordinate is remember that on the plate's surface, your u is 0 because of the no slip condition. And on the edge of the boundary layer, your velocity, the x velocity, is equal to 0.99 times u infinity. So we tend to write that as u infinity outside the boundary layer. And then on the surface, you have your u equal to 0. So again, if I draw the boundary layer for a different distance, again the flow has to go from u equal to 0 to u equal to u infinity at the edge of the boundary layer. So if we define this boundary layer, delta, which is a function of x, you can see that as you move along from left to right, the boundary layer thickness increases. So this boundary layer thickness is a function of x. What that means is that the effect, the shear effects of the plate, the viscous effects because of the plate, they penetrate further into the free stream as you increase your x or as you go further from left to right. It gives more chance as the molecules go from left to right, then they have more time to interact with the molecules above them, and then the boundary layer thickness slowly increases. It's similar to what you had the idea of penetration depth of the momentum in this case. So we define this delta as 0.99 or 99% of the plate has penetrated. 99% of the effects because of the plate have penetrated into the free stream. Call this the free stream, and this region is called the boundary layer. All right. And what happens? I mean, what the thing that causes the momentum to transfer from one layer to the other is the shear stress. It's a shear stress that applies a force from one layer to the other, and this shear stress again, you remember from quantum mechanics that shear stress is a tensor, stress is a tensor, and shear stress is the deviatoric part of that. But here we're just talking about tau yx or tau xy because they're the same because of the symmetry of Cauchy stress tensor. It's the stress in the force in the x direction on the plane which is perpendicular to the y direction. So this tau yx or this tau that we write here is given as your dynamic viscosity mu times del u by del y. Again, this is something you already know. And as engineers, the most important thing that you would want to calculate from this whole boundary layer analysis is the shear stress on the wall. Because when a fluid flows over a surface, it applies a friction. The surface applies a friction force on the fluid and vice versa. So we want to calculate that because if you want to continue the fluid to flow on the surface with the same speed, then you'll have to maintain some sort of flow, and that to maintain that flow, you need some pumping power. Okay? Or if you have stagnant fluid and your solids moving through the fluid, like a car moving through ambient air, then to maintain the same speed of the car, you have to ensure that the engine applies a constant force, which is equal to the friction force that the air applies in the car. So we have to calculate the friction force. That's the most important thing as engineers that you want to calculate on the in this analysis. So that's called the wall shear stress. That is mu times del u by del y at y equal to 0. So that's the most important quantity that you want to calculate. And once you have the wall shear stress, you can multiply that by the surface area, or if the tau wall is changing as a function of the x value here, then you integrate over the whole surface area to get the force. The force is shear stress times the area integrated. And this, I'll write, this then is used to calculate your skin friction coefficient, which is simply a non-dimensionalized form of the wall shear stress. So you divide the tau wall by half times density of the fluid times the free stream velocity squared. And what we also see, again, we saw that in fluid mechanics, that the wall shear stress, well, not the wall shear stress, the shear stress in general, what we see that as your y increases, what that means is if I go, let's take this situation. If I go up, then my velocity gradient del u by del y is decreasing. The parabolic variation. So at the surface of the solid, your del u by del y is maximum, as you can see from the slope here. And as you go up, the slope is decreasing, and ultimately it becomes 0. We're talking about del u by del y. So think of the slope as that. You have to rotate the figure 90 degrees and then see the bottom, and then you'll understand that. So del u by del y, so as, let's write that, as y increases, your tau decreases. The shear stress, but shear stress exists inside the fluid as well. So shear stress at the surface, the fluid layer touching the surface of the solid is the maximum. And as you go up, it becomes 0 at the boundary layer and beyond, at the boundary layer surface and beyond it. And remember, the shear stress is what causes the momentum to transfer. So one layer is moving at, if you put the solid surface, and one layer at the top is moving at the high speed, then it tends to move the layer below it at high speed. And if one layer below is moving at a low speed, it tends to decelerate the layer above it. It's that shear stress that causes the interaction between layers in the fluid. So the shear stress is going down as you go up in the perpendicular to the surface of the solid. I mean, again, you know these things, but the reason I'm talking about all these, recalling all these things, is because we will have a nice parallel between this page and when I draw the same thing for thermal boundary layers. Okay. Then another thing that we see is as my x increases, that is, as I go from left to right, then my wall shear stress decreases. So wall shear stress, remember, is del u by del y times mu at the surface. That means I'm interested in the slopes at the surface. As you're going from left to right, you can see from this green lines that the slope is decreasing. Again, remember, this is del u by del y. So you have to see the figure rotated 90 degrees from the bottom. this slope's decreasing. So what we're seeing is that the friction that the fluid applies on the solid is very high at the leading towards near the leading edge, and as you go further away from the point where the fluid hits the solid, the friction force it applies in the fluid, solid is reducing. The wall shear stress is reducing. Again, from fluid mechanics, this has a lot of implications. You have to make sure that if for some reason your friction could, scrape off the paint on a surface or damage the surface or do something to it, and you have to make sure that your solid surface is much more resilient and stronger near the leading edge as compared to further away from the leading edge. And again, to calculate the total force, you'll have to integrate along the whole surface, and you will see that the wall shear stress is reduced. And it makes sense because your fluid has to go from zero velocity at the surface of the solid. The fluid has to go from zero velocity at the surface of the solid to u infinity at the surface of the boundary layer. But since the boundary layer is very thin to start with, that means this change has to happen over a small thickness. So that means that the gradients have to be stronger. And near the further away from the leading edge, your fluid again has to go from zero u equal to zero to u equal to u infinity. But that the length available is very long. So that means it can slowly go from u equal to zero to u equal to u infinity. So that slope is going to be much more gentle. Is that clear?
Sir, is the vertical component of velocity zero here?
Well, this is something that we are assuming here. In most boundary layer analysis, when you have a flat plate, for example, if it's an ideal flat plate and the flow enters from left to right in completely u direction, the x direction, then you'll have no u component. If the surface is curved, then these u components will develop. But in boundary layer analysis, we always talk of, even if the surface is curving, we always talk of the component of the flow which is along the direction of the curvature. So we take one component which is always pointing perpendicular to the y line, which is normal to the surface.
Sir, if then the fluid is incompressible, then the gradient of V should be equal to zero. That means du by dx plus dv by dy should be zero. If V is zero, then du by dx should also be zero.
Mhm. You're saying for incompressible fluids, we have this thing, right?
Yes, sir. Then if V is zero, then U will get constant, and it doesn't seem like constant here.
Mhm.
Across axis, it's changing.
Right. So in that case, it's a good point. So you're saying that as we go further from left to right, then my u velocity, u value has to remain constant as a function of x. Right. So this again is the assumption here is that fluid is incompressible. So if it's air we are talking about, then air definitely is going to be compressible. But again, we're talking about a situation, if the velocity of air is much less than the velocity of sound, then we can assume it to be almost incompressible. Okay, I'll have to get back on that. that requires some thinking as to what happens in the case of flat plate.
Okay, sir.
It may happen that you'll get some V velocities generated. So to ensure that this compatibility condition of del u by del x plus del v by del y has to be satisfied. I'll get back to you on this one. In any other question?
This will only happen inside the boundary layer. If we like consider outside, then there will be no vertical velocities needed.
Right. Outside we have u infinity, so this condition is nicely satisfied. But inside we may have some v developing because of this.
Yes, sir.
Any other questions? So then let's talk about the thermal boundary layer. Okay, so very similar to the velocity boundary layer. So let's assume that you have the same plate. And then you have a fluid that's again flowing across this, and this fluid is at a temperature of T infinity. And this T infinity in this case is cold it's colder as compared to the T surface. Your surface temperature. The plate is hot. You're trying to cool it down by putting it on the path of the cold fluid. What we see is that on the left hand side we have this T infinity. So I use the x direction, these lines to denote the extent of the temperature. The longer the lines, the larger the T infinity value, the temperature value. So just before touching, just before the flow impacts the flat plate, the whole fluid is at T infinity temperature. But when the fluid impacts the flat plate, you see that again a boundary layer develops. But in this case, we're talking about the boundary layer of temperature. The boundary layer, anyways, is a hypothetical concept. So in this case, we're talking about the thermal boundary layer as a function of x. What that means is that on the surface, you have Ts as a temperature. I'll denote that by a small length. And on the edge of the boundary layer, you have a large temperature T infinity. And then the temperature develops, or the temperature varies from Ts to T infinity as you go up along the away from the surface in this case. And as we move further from left to right, just as we had in our velocity boundary layer, we see that the fluid gets a longer distance to go from Ts to T infinity. So what that means is that the gradients we'll see will be lesser as we go from left to right. And this time we're talking about the gradient of temperature, and that too on the surface.
So longer line means less temperature or higher temperature?
Longer distance means that the gradients are smaller.
Okay.
We're always going from T surface to T infinity. So all these lines that we have on the top are the same length, T infinity, and we go from Ts. So let's see this Q, which is the rate of heat flow from the surface, is written as minus K fluid. So we're talking about that first layer of fluid just above the solid surface, and in this first layer we only have we only have conduction happening. So we have minus K fluid times the area. So we're talking about some area through which this is happening. And then we have del T by del Y at Y equal to 0. Okay, so this is the rate of heat flow from some area. Well, in this case, we can assume the area is small because otherwise your del T by del Y will change if you take a longer area. This is the rate of heat. And again, as engineers, it's very important to know the value of the rate of heat flow. That's the only thing we need to find out in heat transfer. Now, in fluid mechanics, the equivalent of this Q was the wall shear stress. The wall shear stress was dependent on the gradient of velocity at y equal to 0, and the rate of heat flow is dependent on the gradient of temperature at y equal to 0. And this Q is also equal to, right here, this Q is also equal to H, that is the heat transfer coefficient, times the area, the same area through which we're talking about the conduction, and then T surface minus T infinity. So when we talk about convection, we don't really worry about the mechanism, etc. that's happening. All we say is we don't worry about the boundary layers and all. We simply model that using the Newton's law of cooling. So the whole effect has been modeled into this H. H times A times the delta T between the surface and the free state. Okay, so this is how we define H. The H gets defined as minus Ks so same, we call this free stream, and this we call the boundary layer region. But again, remember that this is for the temperatures we're talking about. Okay, so this is the definition of our convection heat transfer coefficient. Again, in this case, I use the word subscript T to denote the temperature boundary layer. And remember that this temperature boundary layer may not overlap the velocity boundary layer. So we will, in the next few lectures, we'll talk about the same way we learned about the Blacher's solution to find the velocity boundary layer thickness. We'll also use the same ideas to find the temperature boundary layer thickness, and then we'll see that they're not the same. But let's be clear about this. And again, how do we define this temperature boundary layer? So delta T is defined in such a way so that 99% of the effects because of the surface have penetrated into the fluid. So, the maximum difference between temperature that we have here is T infinity minus Ts, and we're talking about 99% of those effects being penetrated. So we call that T minus Ts is equal to 0.9. Okay, so if you go further and further, let's say that this is 99% at a distance here, which is the boundary layer thickness. And if you go further away from this, further up from here, then your T will go closer and closer to T infinity, and this ratio will tend further towards 1. Okay, but we are happy to define the boundary layer thickness where 99% of the effects because of the surface have penetrated into the free stream. Is that clear?
Sir, if the Ts is greater than T infinity, then the temperature distribution will be different.
Right. That will be different. Did I draw it the wrong way?
Yes, sir. Yeah, you have written Ts greater than T.
Sorry. Well, in this case, I should then, rather than changing the whole figure, I'll simply say this is the case where T infinity is greater than Ts. So, so we're trying to heat a solid surface by allowing hot air to flow over it. That is also quite possible. Otherwise, I'll have to change. But in case it was the other way around, then you'll have something like this. You go from 3 infinity to yes. So that is when your T infinity is less than. Okay. Now let's see what ideas we discussed in the velocity boundary layers. So we talked about the fact that as my y increases, my tau decreases. Do we see the same thing, similar thing here? As my y increases, then remember the equivalent of tau is q. Okay? So q is dependent on del t by del y. If I look at one situation, which is let's say this one. So as I go further up, what I'm seeing is that my slopes are changing. Okay? So in this case, I should have drawn it. It's very difficult when I compare these slopes. Let's exaggerate them. Let's use a different page. Let's use the case where we are cooling the plate down. It's much more easier to draw these effects. Yeah, two cases are enough. So this is my y. So as my y increases, so what you're seeing is, in this case, let's take this one. So as your y is increasing, your slope that you have in this case is becoming gentler and gentler. Remember, this is we're talking about del t by del y. So t is in this direction, and y is in this direction. So we see that as y increases, del t by del y decreases, and that means my q is also decreasing. But again, that's and the other thing we talked about was as my x increases. In this case, you have this x coordinate along the plate. So as your x is increasing, the gradients of temperature on the wall, which is this one. So if I compare this line with this line, then I see that the gradient on the wall is also becoming gentler. That's del t by del y is decreasing, or your q is decreasing. Okay. Again, very similar to the ideas in fluid mechanics. So as you go from left to right in the plate, then the rate at which you lose heat from the surface of the plate is decreasing. Okay, so the heat loss from the area close to the leading edge is very high, and as you go along further, the rate of heat loss is much less. Okay, so if for some reason you had to maintain a constant plate temperature, let's say now the plate is losing heat, and because of that the plate may get colder. But if you did not want that, you wanted the plate temperature to maintain constant at a constant temperature, then you would want to have heaters attached in such a way so that these heaters provide heat to different parts of the plate differently. Otherwise, if you have a constant heat addition at all the different parts of the plate, then you will not be able to maintain the same temperature, because the heat loss at different points in the plate is different with X. Okay. Any questions?
Sir, here the Q is defined at y is equal to 0, but if
Right,
v
right,
is increasing,
right. So that is the reason I was a bit reluctant to talk about Q here. So,
then we will have to consider velocity also, velocity and uh, gradient of t, something like that. Conductive part
for
of
conduction or
differential
convection?
equation. Yeah, convection part of differential equations, like v into dt by uh, dx kind of thing.
So now that I've removed this Q from the picture, does that part is that part clear?
Yes, sir. Yeah.
So we don't want to talk about the heat flow further away from the plate inside the fluid, because that becomes a complicated discussion, and we don't want that. Right now, our discussion interest is only in what's happening from the surface of the solid because of convection. Okay. So let's only talk about the Q at the surface because of convection here. Okay. So now that we have an H defined, which is which of course in this expression for H, Th minus T infinity is a constant. It does not change along the x or y, well, along the x direction in the plate. Kf also is a constant. So my H only depends on my del T by del y at y equal to 0. Instead of talking about the rate of heat flow Q, we tend to talk about the H values. Okay, so we try to understand how my H changes as I go further from left to right in a flat plate or any curved plate as well. So what we say is that as my X increases, my H, what do you think? Is my H increasing or decreasing with increasing H? The increasing X, sorry.
Decrease. Decrease.
Okay. So the heat transfer coefficient decreases as you go further in this solid and along the length of the solid. Okay, this is a flat plate. That's idealization, but the idea is similar for curved bodies as well. So remember that. Remember this idea that your heat transfer coefficient will decrease if you go further away from the surface, from the leading edge of the solid surface. And similarly, your Q also decreases because of convection in this case. Okay. So it's again a same idea as fluid. So as you go further from left to right, the skin friction coefficient reduces. In this case, your heat transfer coefficient reduces as you go from left to right in the plate. I think we're out of time here, so I will stop here and I'll continue the discussion on the heat transfer coefficient as a function of x. We'll solve a problem on that, and then we'll move on to solving the equations of boundary layer like we did in fluid mechanics. In this case, we'll solve for the equations of temperature to find the temperature, how the temperature changes inside the boundary layer, and how to get that temperature variation as a function of y. A profile that I'm drawing again and again is something that we have to obtain by solving the equations of energy. I'll stop the recording. If you have any questions, you can ask.